Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I'm studying in CSE AI and ML, that is Computer Science and Engineering, with the specialization of Artificial Intelligence and Machine Learning, 4th semester, Institute of Aeronautical Engineering. In this concept video of the subject of computer networks, the topic I am going to discuss about is functions of network layer. So let's go through the contents first of all. In the first place, I'm going to introduce the topic. I'm going to give the overview of the network layer and its fundamental role in communication. Next, we'll go through the routing, which means finding the optimal path. I'll discuss about how networks determine the optimal path for data transaction or data transmission. Next, I'm going to discuss about logical addressing and forwarding, the IP addressing and packet forwarding mechanisms. I'm going to discuss about them. And lastly, I'm going to conclude the topic with key takeaways and importance of network layer functions. So let's go through the topic. Now, first of all, network layer. We all know about the OSI model, right? The Open Systems Interconnection model. It has 7 layers: physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. Network layer is the third layer of this, and it is responsible for end-to-end data delivery across multiple kinds of networks. Now, this network layer has 3 main functions. One is routing, that is finding the best path through interconnected networks. Logical addressing, that is IP addressing. IP means we all know, that is a internet protocol. IP layer means internet protocol layer, that is also a part of the internet. IP addressing for unique device identification. This is logical addressing and directing packets to the next destination, that is packet forwarding. These 3 are the most important functions of network layer. It acts as a backbone of inter-network communication, enabling global connectivity such as the internet. Without network layer, communication would be limited to local networks only, making large-scale communication impossible, highly impossible. Hence, this is the introduction. Now let's talk about routing, that is finding the optimal path. The main problem here is that whenever the data is sent from systems, sent across the systems for the purpose of communication, there are multiple possible paths. Choosing the wrong path can cause delays, packet loss, and network congestion. The solution here is that routing algorithms determine the optimal path based on metrics like distance, cost, or time to ensure efficient data transmission. For this, the implementation done in Python demonstrates the shortest path communication using Dijkstra's algorithm, similar to the routing decisions which often happen in networks. So let's talk about what this code does. It implements Dijkstra's algorithm, which is used to finding the shortest distance from starting node to all other nodes in a graph. It works only when the edge weights are non-negative. In the first place, the import statement. Import heap queue. Here, heap queue is a priority queue with minimum heap library. A priority queue library in Python. It always gives a smallest element, the smallest element first. This is very important because Dijkstra always selects the node with the minimum distance. Now let's talk about the function. Here the function is defined as Dijkstra with two attributes: graph, a dictionary representing the graph, and start, the starting node or the source. Now let's talk about the initialization. Q is equal to 0 start, a list and a tuple inside that with two elements 0 and start. The priority queue is initialized with distance 0 and a starting node. That is the queue over there which is initialized. And the distance is over there. Distance is a graph, a dictionary with a node and the float inf for node in graph, and distances start. The start point in the distances is equal to 0. That's what we are initializing here, which means creating a dictionary to store shortest distances. Initially all nodes are infinite. Start node is 0, which means we don't know the distances yet. We don't know the distances except the starting node. Here the main loop, the core logic. While queue, that means to run until the queue becomes empty. Step 1. Get the closest node. Current distances current loop is equal to heap queue dot heap pop queue, which means remove the node with smallest distance. This ensures we always process the nearest node first. Step 2. Explore all kinds of neighbors around. For neighbor and weight in graph current node, we have to that means we have to look at all adjacent nodes. Each neighbor has neighbor as node name, and weight, the edge cost. Step 3 is to calculate the new distance. For the distance, the current distance plus weight is considered as the distance here. Here the total distance is equal to current path plus edge weight. Step 4. Step 4 is that we have to update if shorter path found. If distance is lesser than distances neighbor, we have to check if this new path is better, and then distances neighbor is equal to distance. Here we update the shortest distance. Heap q dot heap push q distance neighbor. Here we added an updated node back into the queue so that it can explore further paths. Return result. Here the entire code returns the distances. It returns the shortest distance from start node to all nodes. The graph representation. First of all, here the graph we chose, it is a network of 4 systems: A, B, C, D. Between A and B there is a distance of 1 unit. Between A and C there is a distance of 4 units. Between B and C there is a distance of 2 units. Between B and D there is a distance of 5 units. Between C and D there is a distance of 1 unit. This is an adjacency list. Here D has no neighbors. Here the function call. We are calling the function print Dijkstra graph A, and to start from the node A, the step-by-step working is that in the initial place the distances are A is equal to 0, B is equal to infinite, C is equal to infinite, D is equal to infinite, Q is equal to 0, A. In the first iteration, visit B, distance is equal to 1. Visit C, distance will be equal to 4. Distances are A is equal to 0, B is equal to 1, C is equal to 4, D is equal to infinite. The Q becomes 1, B, 4C. In the second iteration, visit C, 1 plus 2 is equal to 3, that is better than 4. Visit D, 1 plus 5 is equal to 6. Hence the distances A is equal to 0, B is equal to 1, C is equal to 3 and D is equal to 6. They get updated like this, and the Q is 3C, 4C, 6D. In the third iteration, visit D, the 3 visited before plus 1, it becomes 4, that is better than 6 in the previous iteration. Hence the distances become A is equal to 0, B is equal to 1, C is equal to 3, D is equal to 4. And the Q becomes 4C, 6D and 4D. Hence the final output becomes A0, B1, C3 and D4. Here the time complexity is using heap, the priority queue, that is big O of V plus E log V. Here V is equal to number of vertices, E is equal to number of edges. Hence the overall one line summary is that this code finds the shortest distance from a source node to all other nodes using Dijkstra's algorithm with a priority queue for efficiency. Hence this is all about routing, finding the optimal path. Now let's go through logical addressing and forwarding. Here the main problem is that the devices need a unique identification system across global networks. Routers must also decide where to send each packet next to reach its destination. The solution of this problem is that logical addressing assigns unique IP address to devices. Packet forwarding examines addresses, destination addresses, and routes packets based on routing tables. The logical addressing is that each device is assigned a unique IP address. For example, 192.173.10 or any such kind of IP address in order to identify the source and destination hosts. The packet forwarding, by definition, it is that routers examine the destination IP address and forward packets to the next hop based on routing tables. Let's simulate this entire process in Python. A clear explanation. This is a simple simulation of packet forwarding in computer networks done in Python. Let's talk about this code. This code represents a basic function. It simulates a basic function of the routing table in packet forwarding. In real networks, routers decide where to send a packet based on destination IP. This decision is made using a routing table. Let's define a routing table. Here in Python, it is defined as a dictionary with a key value mapping. The destination is a destination. If a packet wants to go to any IP, then the program is to send it to the respective router. This is the concept of routing table and packet forwarding. Let's define a function. The function here is defined as forward underscore packet. The attribute here is destination underscore IP. This function simulates packet forwarding. It takes destination underscore IP where the packet needs to go. Let's take a condition, the core logic. If destination underscore IP in routing underscore table. Here the program checks if the destination exists in routing table. It is equivalent to the question that if we know where to send this packet. Basically, it checks the destination. If any route exists, it returns the packet forwarded to the destination. It looks up the router from dictionary. It returns the message. Hence, the message overall sent, it comes packet forwarded to the router and the router number or the router ID. Router A, router B, router C, any ID. But if the route does not exist, the else return destination not reachable. The code, it means that if no route found, the packet is dropped. And after all this, we are calling the function print forward underscore packet 192.168.1.2. Yes, step by step. Let's go through a step-by-step explanation for this. Here the input, the router, it is found in the routing table. It maps to router B and output becomes packet forwarded to router B. Now let's discuss about the real world applications of this concept. Routing underscore table. It is the router's routing table. Destination underscore IP. It is the IP address of the packet's destination. Forward underscore packet. It is the logic to forward the router, and the return message is the forwarding decision. An overall summary. This code simulates how a router forwards packets using a routing table by matching the destination IP with the next hop router. Hence, this is all about logical addressing and forwarding. Now let's go through the next slide. Now let's go through the conclusion. Let me finally conclude the topic by saying that the network layer enables communication across interconnected networks through three essential functions: routing, logical addressing, and packet forwarding. It ensures data is transmitted efficiently, reliably, and through the best possible path from source to destination. Without this network layer, modern communication systems like the internet would not function, making it a fundamental concept of computer networks. Hence, this was all about the functions of network layer. And now finally, I would like to sincerely thank the respected professors to give this wonderful opportunity to me to speak upon this wonderful topic. Thank you.